Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 4 on computing Taylor series.
We now have in hand the definition of the Taylor series, but the question remains, what is the best way to compute them? In this lesson, we'll cover some methods for clean and quick computations of Taylor series. In doing so, we'll see that this leads us to some new and interesting functions.
Recall the definition of a Taylor series. If you want to compute one of these, well, you may have to take a lot of derivatives, but that's not your only choice. There are a few other methods as well, including substitution and combination. Let's begin with an example that displays a substitution method. Consider the function 1 over x times sine of x squared. Computing the Taylor series for this might be a lot of work. Having to differentiate this is not entirely trivial. However, we do know what sine of x is in terms of its Taylor series. Sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. If instead of using sine of x, we use sine of x squared, plugging in x squared into the Taylor series for sine of x, and then multiplying that by 1 over x, well, we obtain something that is going to work. A little bit of simplification gives x minus x to the 5th over 3 factorial plus x to the 9th over 5 factorial, etc. Another method for obtaining the same answer would be to take the full summation as k goes from 0 to infinity of -1 to the k times x squared to the 2k plus 1 over 2k plus 1 quantity factorial. By adding up the coefficients of the x term properly, we can, in fact, obtain the full Taylor series for this function as sum k goes from 0 to infinity, -1 to the k, x to the 4k plus 1 over quantity 2k plus 1 factorial. That means, in effect, that we have all of the derivatives of this function evaluated at 0 in one simple computation. There are other methods as well involving a combination of like terms. Consider the example of cosine squared of x. We know the Taylor series for cosine of x. It is the familiar 1 minus x squared over 2 factorial, etc. We can square that and then evaluate the product. How would we do so? If we consider these as very long polynomials, then we can apply what we know from polynomial multiplication. The lowest order term is equal to 1, that is 1 times 1. The next order term consists of 1 times -x squared over 2 factorial plus -x squared over 2 factorial times 1. The next order terms are of fourth order and consist of x squared over 2 factorial quantity squared. But there are a few others as well. There is an x to the 4th over 4 factorial term and another x to the 4th over 4 factorial term. All of the other terms are going to be of higher order. One could continue multiplying, although the multiplications would become a bit tedious. And now one must simplify these terms. With a little bit of work, it's easy to get the low order terms and to get 1 minus x squared plus x to the 4th over 3 minus x to the 6th times 2/45, etc. If you want more terms, you're going to have to do a bit more work. One thing that you can note, however, is that this must be 1 minus sine squared of x. And so from this, we obtain the Taylor series for sine squared of x as well. With these tools in hand, let us consider a new class of functions. These are the hyperbolic trigs. The hyperbolic cosine of x, or cosh of x, is defined as e to the x plus e to the minus x over 2. The hyperbolic sine of x is defined as e to the x minus e to the minus x over 2. What do these functions look like? Well, they don't look anything like a sine or a cosine. They both grow very rapidly in x due to the exponentials in their definitions. Nevertheless, these are very important and useful functions. There are others as well, such as the hyperbolic tangent, or tanh of x. As you might guess, this is really sinh of x over cosh of x, that is, e to the x minus e to the minus x over e to the x plus e to the minus x. Now, some of the rules that you're familiar with from trigonometry hold in this hyperbolic setting, but with a bit of a twist. For example, cosh squared of x minus sinh squared of x is equal to 1. One can compare that with the familiar formula cosine squared plus sine squared equals 1. What does this formula mean? Well, we know the relationship between cosine, sine, and points on a unit circle. Namely, cosine is the x-coordinate, the sine is the y-coordinate of a point moving along that unit circle. In the hyperbolic trigonometric setting, the same is true, but for a hyperbola instead of for a circle. As you might suspect, there are also hyperbolic secant, cosecant, and cotangent functions. Let's investigate these hyperbolic trig functions from the point of view of Taylor series. For example, if we consider the hyperbolic cosine of x as 1/2 e to the x plus 1/2 e to the minus x, then it's clear how to compute the Taylor series. Instead of trying to take derivatives, we'll simply substitute in the known series for e to the x, multiply by 1/2, and then add to it 1/2 times the series for e to the minus x, which, of course, is the Taylor series for e to the x with minus x substituted in, leaving negative signs at the odd powers of x. By combining terms according to degree, we see that all of the odd degree terms cancel, and we are left with only the even degree terms, the same as in the expansion of e to the x, 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial, etc. If we wish to write this out in summation notation, it would be the sum k goes from 0 to infinity of x to the 2k over 2k quantity factorial. Notice that just like the Taylor series for cosine of x, cosh of x consists of the even powers, but with no alternating sign. That is another relationship between the trigonometric and the hyperbolic trigonometric functions. Does the same hold for the hyperbolic sine? Well, let's investigate and see. Following the same method as before, we'll use the Taylor series for e to the x, and then the Taylor series for e to the minus x. But now, instead of adding these two terms together, we are going to subtract the latter from the former. This leads to a cancellation of all the even-powered terms. And distributing the minus sign through and adding, we obtain all of the odd degree terms in the Taylor series for e to the x. Thus, the sum k goes from 0 to infinity of x to the 2k plus 1 over 2k plus 1 quantity factorial, just like sine. We can continue our exploration of these functions by proceeding as if the Taylor series are like long polynomials. Hence, computing things like integrals or derivatives can be done term by term. Let's consider what the derivative of the hyperbolic sine of x would be. Well, we can differentiate the terms of the Taylor series. Since the derivative of x to the 2k plus 1 equals 2k plus 1 times x to the 2k, we can see by dividing by 2k plus 1 quantity factorial and summing as k goes from 0 to infinity, that the derivative is the sum, k goes from 0 to infinity, of x to the 2k over 2k quantity factorial. That is simply the hyperbolic cosine of x. In similarity to what happens with trig functions, the derivative of sinh is cosh. Likewise, what is the derivative of cosh of x? If we differentiate term by term, we can see that the derivative of x to the 2k is 2k times x to the 2k minus 1. Now we have to perform a shift in the index here in order to avoid problems with what happens when k equals 0. Reindexing properly gives us the sum, k goes from 0 to infinity, of x to the 2k plus 1 over 2k plus 1 quantity factorial. That is the hyperbolic sine of x. And so we see that the hyperbolic trig functions are very nice. The derivative of sinh is cosh, the derivative of cosh is sinh, and this becomes clear from the Taylor series. Now, we're used to writing out the Taylor series term by term. Of course, since there are infinitely many, we can't write them all. We typically use a plus dot 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 or an ellipsis to connote what happens in the tail of the series. But there's another terminology that we will begin using, that of HOT, or higher order terms. This is an informal way of saying etc., and it can be a bit helpful. For example, you might say that cosine of x is 1 minus x squared over 2 plus higher order terms. We could say that sine of x is x plus higher order terms, or x minus x cubed over 3 factorial plus HOT. We could stop whenever we feel like. That's a convenient thing to do when performing computations on Taylor series. We'll use a more formal bookkeeping mechanism soon. Let's look at this in the context of a simple example. 1 minus 2x times e to the sine of x squared. We'll begin with the Taylor series for sine of x squared, which is simply x squared minus x to the 6th over 6 plus higher order terms. What happens when we exponentiate this? We use the Taylor series for e to the x. 1 plus our quantity above plus 1/2 times that quantity squared plus 1/6 times that quantity cubed, etc. Notice that I'm using plus higher order terms liberally in order to ignore things that aren't going to matter for the first few terms. To simplify this, we go degree by degree. The constant term is 1. There's only one quadratic term, namely x squared. Are there any fourth order terms? Well, yes, there is. 1/2 times x to the 4th. In the 6th degree terms, there are 2 of them, but notice that the coefficients balance each other out, and so the coefficient of the 6th order term is 0. We are left with a Taylor series of 1 plus x squared plus x to the 4th over 2 plus higher order terms. Now, to get the Taylor series for our original function f, we simply take 1 and subtract 2x times the quantity obtained above. I'll let you show, with a little simplification, that this is 1 minus 2x minus 2x cubed minus x to the 5th plus higher order terms. If you want more terms, you can get them. It will take more work.
We've now learned not only what Taylor series are, but how to compute them quickly and cleanly. Along the way, we've been introduced to two new characters in our story, the hyperbolic sine and cosine. In our next lesson, we're going to consider what happens when things don't work out so well. We'll deal with issues of convergence.